We have two identical capacitors of capacitance C connected in series to a battery of voltage V. Right now there's some potential energy stored in our system. Now the question is, if we insert dielectric material in one of the capacitors, how does that change the stored energy in the system? To answer this question, we're going to calculate or find an expression for the potential energy without dielectrics, and then we'll find an expression for potential energy with dielectrics and compare the two. Here's my formula for potential energy. It's equal to 1/2 C equivalent times V squared. I'm using labels initial to indicate that this is a calculation corresponding to before we insert the dielectric material. Now note that I don't have any labels for voltage V because the voltage does not change. What changes when we insert the dielectric is going to be the equivalent capacitance, and the energy will change accordingly as well. So first thing first, let's go ahead and calculate the equivalent capacitance before the dielectric is inserted. We apply the equivalent capacitance formula for series connection. We add the reciprocals of capacitance values and then take the inverse. 1/C plus 1/C, that's 2/C. Take the inverse, you get C divided by 2. So that's our equivalent capacitance. Now let's use this value to calculate the initial value of potential energy. We substitute C/2 for equivalent capacitance and simplify. We get CV squared divided by 4 for the initial potential energy. Next, we insert the electric material of the electric constant K in between the plates of one of the capacitors. So that's the one on the left hand side. Now, what happens to my capacitor? Its capacitance will change and it'll be equal to K times C. So K times the original value. Let's recalculate the equivalent capacitance with the dielectric inserted. Here I have set up my formula for equivalent capacitance. Note that I'm using the label final for this one. And also note I have a factor of K for the first capacitance value. Now I'm going to add these two fractions, and for that we need to bring them to a common denominator. So I'm going to multiply and divide the second fraction by K. So 1/C will become K divided by K times C. And then add the two fractions. And here's what we get when we complete the calculation. Final equivalent capacitance is equal to Kc divided by 1 plus K. Now let's use this result to recalculate the potential energy stored in our system. And here's what we get when we use the final value of the equivalent capacitance and recalculate the potential energy. Next and the last step will be to find the ratio of U final divided by U initial. So this will tell us by what factor the potential energy has changed. So both of the expressions for the initial and final values of potential energy are relatively heavy. So for this calculation, I'm multiplying U final by the reciprocal of U initial, which is equivalent to doing U final divided by U initial. Now here's what we have, and we see that a lot of the variables cancel. C's cancel, V squares cancel, and the 4 in the numerator simplifies the 2 in the denominator. And here's what we get after the simplifications. U final is equal to this expression in parentheses times U initial. Now, has the energy increased or decreased? K is greater than 1, so 2K divided by 1 plus K overall is going to be greater than 1. Therefore, U final is equal to U initial times some number greater than 1. So U final is greater than U initial, meaning after we have inserted the dielectric material, the energy stored in the system has increased. Does that mean we get some extra energy out of nowhere? Absolutely not. The system is gaining energy because we're doing work on the system as we're inserting the dielectric material.